Welcome to day 14 and congratulations on completing week 2 of your STL journey. You have now covered 5 essential containers: DQ, list, stack, queue, and priority queue. Each of these plays a crucial role in real world problem solving. Today is about revisiting what we have learned, reinforcing the key concepts, and testing your knowledge through an interactive quiz. The goal here is not just to memorize, but to deepen your understanding and build confidence as we move into more complex STL containers in week 3. Let's dive in. Let's start with the DQ, short for doubly ended queue. What makes it unique is that it allows you to insert and remove elements from both the front and the back. This gives it a performance advantage in many scenarios where both ends of a sequence need to be accessed efficiently. Under the hood, a DQ uses a segmented dynamic array. This means it does not reallocate memory as frequently as a vector when resizing, especially at the front. You will often see DQ used in problems like the sliding window maximum, where you need quick front and back operations. Think of it as a flexible and efficient alternative to vectors when two end access is required. Next up, we have the STL list, specifically a doubly linked list. Unlike vectors and DQs that use contiguous memory, a list is made of nodes that are spread out in memory and connected through pointers. This structure allows for extremely efficient insertions and deletions, especially in the middle of the list, something that vectors and DQs can't do efficiently. However, there's a trade-off. Since the elements aren't stored in a contiguous block, you can't access them randomly with square brackets. You have to traverse the list using iterators. Use lists when your operations involve frequent modifications, especially in the middle of the sequence, and not when you need fast access by index. Now let's review the stack, a classic last in first out or LIFO structure. This container is extremely useful in problems that require backtracking, recursion simulation, or tracking nested structures like brackets or function calls. The key functions are push to insert, pop to remove, and top to view the last inserted elements. Internally, a stack can be implemented using a vector, DQ, or even a list, but it restricts access to only one end, the top, so you can't iterate or access other elements directly. If you need to examine elements, you will have to pop them off one by one. Think of it as a controlled access container that mirrors real-world stack behavior. Let's cover two more containers, queue and priority queue. A queue is a first in first out or FIFO structure, just like a line at a store. You insert at the back with push and remove from the front with pop. It's ideal for task scheduling, process management, and breadth first search. On the other hand, a priority queue is a container that always gives access to the element with the highest priority. By default, it behaves like a max heap, meaning the largest element is always at the top. But with a custom comparator, you can turn it into a mean heap, useful for Dijkstra's algorithm or when you need the smallest element. Internally, a priority queue is backed by a vector and uses heap algorithms to maintain order. Now let's look at some common mistakes students often make when working with these containers. First, never access the top of a stack or the front of a queue without first checking if the container is empty. Doing so could lead to crashes or undefined behavior. Next, remember that list does not support square bracket access. It's not an array. Another common misconception is thinking that a priority queue is fully sorted. It's not. Only the top element is guaranteed to be the highest priority. The rest are in heap order. Finally, it's easy to confuse front and back when working with DQs, especially when popping elements from both ends. Watch out for this. They can trip you up during coding or interviews. Alright, it's time to challenge yourself with a quiz. This one has 10 questions that mix theory and practice. There are 5 multiple choice questions to test your conceptual clarity, 3 output based questions where you will predict what a piece of code will produce, and 2 debug the code problems that require spotting and fixing logical or syntax issues. Take your time, pause the video if needed, and really try to solve them before checking the answers. This is your checkpoint to ensure you are truly grasping what we have covered. Let's go through the quiz together. For each question, I will give you the correct answer and explain the reason behind it. This isn't just about being right or wrong, it's about learning why. We will also highlight common mistakes and clear up any misconceptions. These explanations will strengthen your conceptual foundation and prepare you better for real world coding, interviews, and contests. Looking ahead to week 3, we are entering the world of associative containers. This includes sets and maps, both in ordered and unordered forms. You will learn how to store key value pairs before lookups in constant time. Even customize how elements are compared using custom comparators. We will also take a deep dive into iterators, a critical topic that empowers you to traverse containers effectively. Week 3 also includes a mid-course quiz to evaluate your learning progress. It's going to be an exciting and intellectually rewarding week. You have done a phenomenal job completing week 2. These containers you have studied from the foundation of efficient problem solving in C++. Remember, mastery isn't about rushing. It comes from repeating, reflection, and application. So keep practicing, code daily, review what you have learned, and tackle real problems from platforms like LeetCode or Codeforces. And most importantly, stay curious and don't be afraid to ask questions. You are building a strong code toolkit that will serve you throughout your software development journey. Let's keep going and make week 3 even more awesome.